In this unit, we'll begin our discussion of magnets, and we're going to discuss the force of a magnet and how it's related to current and electricity. But before we do that, we do need to have a pretty good understanding of what a magnet is. And a magnet is composed of poles. It has a north pole and a south pole. And if you have a magnet that you don't know which end is which, you don't know which end is north, which end is south, it's easy to tell. Just suspend that magnet from a string and it will automatically align itself with Earth's magnetic field. And the part of it that points north is the north pole of that magnet. Okay, so if you suspend a magnet from a string, it will align itself along Earth's magnetic field lines, and the north pole of the magnet points north. So the south pole of the magnet will be pointing south. Magnets are capable of exerting forces on other magnets, and they do that over a distance, so it's a field force. So this is sort of like an electric force that's a field force as well, but it is different because you can take an electron and separate it from a proton, so you can separate negative and positive charges. You cannot do that with a magnet. Okay? Magnets always have both poles. Always. Okay? Nobody's ever been able to separate the north pole from the south pole. Nobody's ever had just a north pole anywhere. So magnets always have both north and south poles. So if you were to take a bar magnet and cut it in half, you would have started with a magnet that had a north pole and a south pole, and then you would break that in half and you would have a magnet that has a north pole and a south pole, and another magnet that also has a north pole and a south pole. And if you were to take these two pieces and lock them together, then you would have back to a single magnet with a single north pole and a single south pole. So a pole cannot be isolated. You can't have just a north pole. Much like electric forces are represented with fields, we do draw magnetic field lines to represent the field around it. And these are similar to electric field lines. We'll look at how these are drawn. So if you take a bar magnet, it's got a north pole, it has a south pole, and a magnetic field line, it's easy to plot out. If you take a compass and you start it right here at the north pole, then the north side of that compass is going to point this way. And then if you move the compass to that dot, the north pole is actually the compass is going to point this way. And then if you move it, it's going to point this way. And then it'll point this way, this way, this way, this way, this way, and it'll start to curve back around towards the south pole. And in fact, that's actually how we draw or determine the direction of a magnetic field. We look at which way a compass points when we place it near the magnet, and the direction of the compass tells us the direction of the magnetic field line. So they emanate from north poles and they come into south poles, and unlike a charge, this field line actually continues right through the magnet. So it looks like that, and on this side it loops out like this. And much like charge, the lines per area indicate strength. Okay, so if there's more field lines in a given area, then it's a stronger magnet, and the direction is direction a compass points. Okay, but it is interesting to note that that direction is tangent to these field lines at any point. Okay, so right here, this compass is going to point this way, so it's tangent to the field line. And because we have magnets that can interact with other magnets, we can take a look at what these field lines would look like if we brought two similar ends or dissimilar ends together in between magnets. So if I take a north pole and a south pole, what we get is a field line that jumps more or less straight across. There will be some bulgings at the edges, but this gives us a uniform magnetic field, which we'll be looking at those a little bit. They're easier to deal with. If you brought two north poles next to each other, north next to a north, this is like bringing two positive charges next to each other. The field lines are going to bend away from each other, and you'll get something that looks like that. A south-south would look the same, except the direction, of course, would be reversed. Okay? That's pretty straightforward stuff. Field lines, not so bad. Now, it is the case that you can actually create a magnetic field by having electrons move through a wire. So current creates magnetic fields. Remember, current is the flow of charge. And you guys did an investigation in lab where you took a long straight wire and you put current through it. We'll say the current was flowing this way. So from the positive side to the negative side. That's the direction of conventional current. And I had you measure the strength of the magnetic field. And it was stronger the closer it was to it, and as you moved further away from it, that field got weaker and weaker and weaker. Which makes sense, right? Because as these field lines expand out and move around this magnet, they do have to cover a greater distance. And so as you get farther from the magnet, the strength of the field the strength of the force is going to be less. So out here there's less lines per unit area, in closer there's more lines per unit area, so it is stronger. Okay. The other thing we want to talk about here is what's the direction of this field. And if you take a compass, and this is usually to do with a vertical wire, if you take a compass and you place it next to it, so like this is coming out of a sheet of paper or a plane, and you take a compass and put it here, and then put it here, and then put it here, and then put it here, that compass is actually going to point in the direction of the magnetic field. And you'll notice that this magnetic field actually goes in a circle around that wire. And there's a rule called the right-hand rule that actually allows us to determine the direction of the magnetic field. What you do is you put your thumb in the direction of the current of your right hand. That's why it's called the right-hand rule. So if you take your right hand and you place your thumb in the direction of the current, and then you curl your fingers around the wire, the direction your fingers curl actually indicate the direction of the magnetic field. You'll notice these magnetic field lines are loops around the wire. And you can increase the strength of this field by increasing the current through the wire. You can decrease the strength of the field by decreasing the current through the wire. Now, there's one more thing I do want to talk to you about magnets, and that's permanent magnets. Okay? And a permanent magnet doesn't require charge to be flowing, doesn't require current in order to maintain its magnetic field. Now let's think about how this works. We know that we saw that when we passed current through that wire, it created a magnetic field, which indicates that it is the movement of charge that creates the magnetic field. And in fact, that's true in permanent magnets as well. And permanent magnets are called ferromagnetic. Ferro just means iron. Most of the magnets that you come in contact with daily, magnetic, are made of some iron alloy or some iron mixture. Ferromagnetic, these are permanent magnets. They maintain their magnetic field whether or not current's flowing. But it is still due to moving charge, moving electrons. Okay? If you recall, electrons orbit the nucleus, so they can zip around the nucleus, but electrons also have spin. Now spin is actually a purely quantum mechanical effect, but we tend to think about it like a planet spinning on its axis as it rotates around the sun. Not a perfect model, but it serves practical purpose here. And if you recall, electrons move in orbitals, and there's 2 electrons per orbital. And the electrons in an orbital always have opposite spins. One spins up, one spins down. Okay? Well, it's this spin of the electrons that actually generates the magnetic field. And since most orbitals have their 2 electrons, those 2 things are going to cancel out, and you actually get no magnetic field. But if you have several unpaired electrons in their orbitals and they all have the same spin, then they're going to generate a magnetic field. And of course, this means that all things actually have the ability or interact with magnetic fields in some way. It's just a matter of how many unpaired or paired electrons they have. Ferromagnetic materials tend to have lots of unpaired electrons that can all spin in the same direction. So if you take a chunk of iron, it's going to have little pieces in it called domains. And each of these domains is going to have its electrons all spinning in kind of the same way, which creates a magnetic field, but the net magnetic field is going to be nothing because these are arranged randomly and they'll cancel each other out. However, by applying an external magnetic field to it, you can cause those magnetic domains to align and turn this piece of iron into a permanent magnet. Okay? So a ferromagnetic thing creates a permanent magnetic field. There's also paramagnetism and diamagnetism. Paramagnetism means that if you place something in a magnetic field, it's actually going to be attracted by that magnetic field. No matter which way you orient it, it will line itself up so that it's it's attracted to that magnetic field. Whereas diamagnetism is going to oppose all magnetic fields. It's going to align itself the other way. And we're not going to get into those two things in very much detail, but all materials can exhibit some kind of magnetic behavior, paramagnetism or diamagnetism.